unlike Nicholas, unfortunately, I don't really have a lot of robot videos or any robot videos for that matter. But I hope to convey to you that hierarchical reinforcement learning is an interesting set of tools for using potentially in robotics applications by showing some examples of what we can do with these. So I won't talk about what reinforcement learning is. What's hierarchical reinforcement learning, though? It's really an umbrella word or term for many different approaches of structuring the behavior of the agents and the models of the agents that focus both on acting as well as on modeling of the world and on planning. And the intuition is very simple. It's that we want to build a level of abstraction that allows agents to explore their environment faster and more safely, and also to learn faster from the data that they acquire. And secondarily, if we are successful in building these approaches, we would have representations that are compositional. So, for example, models that are learned, that already exist, that can be quickly put together to solve new problems or to resolve in case that the problem is changing. And in principle, if we were successful with these kinds of methods, we can improve both the agent's exploration as well as the credit assignment. So there's sort of two different kinds of knowledge that reinforcement learning agents have. One is knowledge about how to act, and the other one is knowledge about how the world works, or models. And we have equivalent things in hierarchical reinforcement learning. Procedural knowledge or acting knowledge is often modeled in the framework of options. That's the assumption I'm going to make in this talk. And options are a generalization of actions that consist of an initiation set, so a condition under which an option can start, an internal policy or way of behaving, which tells what actions are being done as the option is executing, and then a termination condition that tells us how we end. And so if you think of this in the context of, let's say, robot navigation, an initiation set may be that there's nothing in front of the robot. An internal policy corresponding to this would be that the robot can go forward, and the termination condition might be that the robot is too close to another object, in which case it should stop. So a lot of the inspiration for this actually has come from both classical AI, from macro actions and classical planning, as well as from behavioral robotics and hybrid planning and control. Now, in addition to this kind of behavior knowledge or procedural knowledge, we also have predictive knowledge. So predictive knowledge, in our case, is often equated with representing a quantity of interest over time. And in classical reinforcement learning, this quantity of interest is the return. That means what is the total amount of reward that an agent would receive over time, perhaps discounted in order to reflect that we would like to obtain rewards sooner rather than later if we had a choice. And so in traditional reinforcement learning, we have these quantities called value functions. Value function is often conditioned on a policy or a way of behaving, and it tells us what is the expected discounted sum of rewards that the agent receives over time. And there's a lot of interesting theory that tells us that these value functions can basically guide the search for good policies. In hierarchical reinforcement learning, we can broaden the scope of what's of interest. And so what is of interest is going to be called a cumulant. This is a function C that looks at state, action, and next state pairs. It could be a reward, but it could also be, for example, a feature that the agent is paying attention to, or even a vector of features that the agent is paying attention to. And we will model this over time. But instead of thinking simply of discounting, we might think of this as sort of continuing for a period of time and model that period of time through a continuation function gamma. So I'm using here gamma to sort of emphasize the link between this continuation function and what would be a normal discount factor. The continuation function can be dependent on state, but otherwise is still sort of between 0 and 1 and can be thought of as the probability of continuing to make the prediction from the current state. So these kinds of general value functions are basically dependent on a cumulant on a continuation function and also on a policy that the agent is using. And they can be learned just like any other value function using, for example, Monte Carlo, temporal difference methods, all of the usual mechanisms that we have in reinforcement learning. The interesting thing about them is that now we can have many predictions about many different quantities that span many different timescales. And so there are actually a lot of different special cases of general value functions that go beyond usual value functions and include things like expectation transition models, things like option models, so temporally extended option models, successor states and successor features that are often used to sort of model the evolution of the state during the execution of a policy, and things like auxiliary tasks, for example, where the agent might be interested in predicting something in its observation stream, for example. So I'm going to show you a case study that uses both options and general value functions in the context of a concrete task in order to sort of show what we can obtain by using these kinds of tools. This is not a robotics task, but it is a large-scale task, which is to learn to manipulate complex interfaces. And it's based on a set of environments that we sort of open sourced, packaged together last year with the Montreal DeepMind team. It's called Android Env, and you have the link there to the archive paper. So what this set of environments consists of is an emulator for the Android operating system. And on top of this, there are many different tasks that the reinforcement learning agent can perform. Some of them are games, like you see in the bottom row here. Some of them are Google applications like calendar and clock, and even potentially seeing, for example, the Chrome browser, which enables an agent to do many things. Now, how does the agent interact with this? It interacts with essentially the phone screen. And so it can touch anywhere on the screen and it observes the image on the screen. And one way to think about this is that compared to other, let's say, video games that people have used in the past, the observation space is similarly rich because we have these streams of images. But actually, the action space is much, much larger because the native action space really is touching at any pixel that the agent wants. And so one of the interesting challenges for these agents is to actually learn to do anything in this environment. And as you might imagine, if you use the native action space, it will be extremely hard for the agent to even get to do anything interesting by chance, let alone to actually learn how to optimize the reward functions that are associated with all of these tasks. And so what we have done in a recent paper that is currently on archive is to look at options and general value functions as a way to structure the learning of such an agent. And one way to think about the way that people operate the phone is that they have certain gestures, for example, touch or swipe. They can click buttons. So there are certain classes of gestures that they use. And these gestures are then parameterized. And the parameters might be, for example, where do I want to touch? Or if it's a swipe, from where to where do I want to swipe on the screen? And so we built this kind of structure in these agents in order to see whether this would actually enable them to successfully learn how to manipulate these complex interfaces across many different tasks. And in particular, in this case, we use our prior knowledge about how these apps work in order to define 3 classes of gestures: tap, which means you sort of quickly touch and release the screen; swipe, which is moving across the screen; and fling, which is like a fast swipe. And all of these will have particular sub-goals and cumulants that are associated with them. So, for example, if I want to tap, if I successfully tap at the location that I wanted to, and let's say a button gets pressed, the agent will receive a reward for that. And we will have general value functions that predict these associated rewards and returns for the different classes of gestures. And so we can structure internally these agents into a hierarchical structure where at each layer, the agent has a particular set of observations that it sees, and it has a particular set of things that it can do. And its policy is going to be conditioned on goals that are coming from the higher level. So in this particular case, first we're going to choose what kind of gesture we want to do. Then we're going to choose where we want to do the gesture. And then finally, there's going to be a sequence of actual primitive actions that's associated with performing the gesture with those parameters. And each of these layers acts as an independent reinforcement learning agent, and in fact can be implemented with whatever algorithm you prefer. Some of them are using value-based algorithms, some of them will use policy-based algorithms, and they all learn in parallel and independently from each other at all of these different layers of abstraction in order to convey from the higher layer to the lower layer what is desired to do. We use film conditioning. And so these are all sort of film-like architectures, and I invite you to look at the paper if you want to know more about the details. So what I want to show you here is some results that highlight the power of using this type of hierarchical knowledge. So here we're looking at a few different games of varying difficulties in this case, and what you see here is a comparison between using DQN as a flat learning agent compared to using this approach of having a hierarchically structured agent that has these multiple layers of abstraction and learns at all of the different layers of abstraction in parallel. And you can see that in these games, we can obtain significantly better performance. And in fact, in some of the games, like for example, Flooded and Apple Flinger, flat agents don't get anywhere to any kind of level of performance because the exploration problem there is way too hard unless you impose this kind of knowledge. Now, the downside, the caveat, of course, of this work is that we are using quite heavily prior knowledge. We're encoding it into the structure of the agents. I do dream of these agents discovering this kind of structure by themselves. I think we still have quite a bit of work to do in order for that to be able to be done successfully and end-to-end. Now, another thing that I want to tell you about is compositionality. So how do we put pieces of knowledge together once we have them? And in the example that I showed you before, we had sort of very strict hierarchical compositionality in the sense of decisions being made at a higher level and then conveyed through conditioning to a lower level. And you can build multiple levels of a hierarchy in this way. But we can also use other more interesting or sophisticated forms of compositionality in order to synthesize behavior, not just by sort of calling things in a hierarchical manner, but considering the space of policies and considering the way in which they might influence the behavior. So one particular instantiation of this is the idea of having an option keyboard. So the idea here is that we can have options that are associated with particular cumulants. Each option is optimizing for that specific cumulant, but then we might want to consider combinations of these cumulants and quickly synthesize an option that optimizes for that combination. So the analogy is if you had a piano keyboard, you might be able to learn quite quickly how to push individual keys. But really, to make nice music, you need to know how to make chords. And so a chord is a weighting of different keys in some sense. And so, we also can think of weighting these different cumulants in order to provide new goals for our agents. So this relies very heavily on general value functions. We use, in particular, successor feature general value functions that can be quickly evaluated when the agent's goal or cumulant changes. And we use policy improvement, a form of generalized policy improvement. And to sort of illustrate what we get out of this, I will describe this example where we have a circular arena. You have a simulated agent that can move around in this arena. The agent learns 3 options, red, green, and blue. that maximize going in a particular direction, but then we can actually weigh these cumulants with either positive or negative weights. So for example, we might tell the agent, I want you to go away from the red direction by weighing that negatively, or go towards the blue direction and away from the red direction. And by using these kinds of weightings, we can actually synthesize policies that go into all the different directions, all these yellow pie slices in this arena. And compared to just using call and return hierarchical execution, we can have quite a bit better behavior here. So the picture here, the red line is usual flat learning with DPG. The green line is options using hierarchical execution, so call and return execution. And this blue line on top is using this idea of an option keyboard player. The gray area at the beginning is showing the amount of data that we need to spend in order to train our options and the player. And so one thing that I want to emphasize is that in all of these kinds of methods, we usually do pay an upfront cost in order to learn the representation, the options, the initial models, and then we can obtain the benefits. So really these methods are worth pursuing whenever that upfront cost is worthwhile, right? If we can learn a policy from scratch, without paying that cost, that's great. But in many scalable applications, we cannot actually do that efficiently. And finally, I want to tell you a little bit about ways in which we can control more precisely the size of the action or option space and the size of the model space by using this idea of affordances. A lot of this is work that was led by my PhD student, Kimia Ketterpal, and some of it was carried out at McGill and some of it was carried out at DeepMind. Now, what are affordances? Affordances describe what is possible in the environment, and they're quite useful to biological organisms, right? So a person, for example, might understand that a tree affords climbing, maybe to escape from predators or to have fun, but can also provide shelter from the rain. So there's a concept that's defined at the interface between an agent and an environment. And they circumscribe the set of options that are available to the agent. And so I want to show you a particular line of work that we've been pursuing to formalize this idea in reinforcement learning agents. The experiments that I will show you are small scale, but I'm hoping that some of the people in the crowd here might be enticed to try these ideas at a larger scale. So how do we formalize this idea of an affordance? One way to think about it is that when an agent is trying to do some action, it might have some intent. Okay, so maybe the agent is intending to move left in this kind of grid world, okay? Or maybe the agent is intending to change one of the features in its observation space or one of the features in its representation. And so the intent captures intuitively a target state distribution that the agent might want to achieve as a consequence of its action. And when we're using affordances, we actually don't even try actions that are hopeless, right? Where an intent cannot be achieved. So, for example, if there is flat ground in front of an animal, it's not going to attempt to climb anything because there's nothing to climb, right? So the idea is to model affordances through this notion of intent, a target state distribution that the agent wants to achieve, and then to define an affordance relation between states and actions as the set of state action pairs in which the intent is satisfied to some degree. And so, for example, in this grid world, if our intent is for the agent to move left, then the states that are marked and the actions that are depicted through the arrows are part of this affordance. Those are the state action pairs that enable the agent to truly succeed in going left. And so one thing that I want to emphasize is that if we only consider these actions in the states where they succeed, we are going to have a model for these actions that can tell us already that the intent is being satisfied you can think of this model as being approximately causal. And it's also a partial model, because in places where the actions will not succeed, we're actually not even going to attempt to model them. And so this has been formalized in an ICML paper in 2020. Now, how are we going to learn these affordances? Well, it's actually a pretty easy problem because it's a classification problem. We can sort of formulate some intents. That part is something that we assume is maybe given based on prior knowledge, or maybe the agent is discovering that independently. But assuming that the agent has some intent, if it's running around in the world, we can observe what state action pairs lead to that intent being achieved, and then essentially carry out the classification problem where the state action pair is an input. And we then will take into the affordance the state action pairs where the probability of achieving the intent is high. And so this is a supervised learning problem, can be done by collecting data in the environment and training the agent. And once we have an affordance, we can also build an affordance-aware partial model. And this partial model is basically only going to provide a prediction for an action in a state where that action is affordable. And so we are not going to model the entire world. We're only going to model the parts of the world where we think the action is going to succeed. The math here is not really important. I want to show you, though, an illustration of this idea. So here we have a little grid world where the agent is on one side, it's walled off. And we are modeling the left action. And in one case, we have a Gaussian model that is learned through data that is from everywhere in the world of the agent whenever it's striving to do this action. And in the other case, we're only going to learn this model from data where the agent is actually succeeding in doing this action. The class of models is the same in both cases. This is Gaussian models. But what you can see is that if we use data where the action sometimes fails, the model is not really learned exactly correctly. And that's because we're going to have sort of truncation effects where the agent is trying to go left, can't move because it's next to a wall. And that data is still incorporated in the model. And so the model is Gaussian almost everywhere, but around the walls, it's not. And that is going to just distort the parameters. Whereas if we don't even attempt to incorporate that data into the model can be more accurate. And then similarly, if we think about the right action here, a baseline model might predict that if the agent is next to a wall, it can go through the wall because that's the nature of a Gaussian model. But an affordance-aware model will just refuse to make a prediction, signaling that this is not a feasible action. Now, we can actually do this not just with primitive actions, but also with options. We can formulate intents as a function of the trajectory of an option. So they can refer to the option achieving a certain end state. So for example, in this little grid world here, a taxi might want to get to one of these colored states. That might be its intent. But we can in fact also define intents on the entire trajectory. So we may want to say something like, the option is making progress going into a particular direction, or has made at least a certain amount of distance from the initial place. So it's a very flexible formulation. And of course, we are going to think of these intents being satisfied, not exactly, but to some degree. And this degree is going to allow us to control the size of affordance sets. So, we can make everything affordable everywhere, or we can actually require that intents are satisfied to quite a high degree, in which case the size of the affordance sets of option state pairs is going to decrease. And we can learn these affordances. The definition of affordances stay the same. It's just the relation between states and options now. And we can think of this degree of satisfiability as being our control over how many sort of state option pairs do we want for an agent to consider. Now, in this particular little world, we can play around with this degree and see what its impact is both on the affordance set size and on the performance of the agent. So this degree is the sort of threshold here, and each of the lines in the figure is showing a sort of a different setting for this. And if all of the option state pairs are affordable, that makes actually for a very large set And we need a lot of steps in the environment to learn these models in order to be able to have them be useful for planning in this case. But if we really want to decrease the size of these option sets, we play around with the threshold parameters. And we can, in fact, get very compact sets, even more compact than when using a heuristics. And the impact on performance is to really increase the performance significantly, especially at small sample sizes. So the intuition here is that we're going to have models that are partial, but they are much better quality. And also the number of choices is going to decrease for the agent. And so the planning process is faster in this case, both because the agent has better models and because it has fewer choices. So just to sort of wrap up, I think reinforcement learning provides us with a lot of very powerful tools for learning and representing knowledge. I focused today on this hierarchical reinforcement learning ideas of using options and general value functions that can encode knowledge for the agents and can be combined quickly to solve new problems. One thing that I want to emphasize is that hierarchical reinforcement learning is not about getting better solutions. It's about performing trade-offs. In particular, it performs a trade-off between the data efficiency, so the amount of data that we're going to need to get to a reasonable performance, the computational efficiency, right, especially in the case of planning, how many iterations do we need to do, and the performance of these agents. The way that I think about it is that, while at the moment we're still using these tools in order to build in a lot of prior knowledge, ideally in the long run, we will learn these representations in service of optimizing the true reward function in the environment. And I think there's a lot of interesting work to do in that direction. So I'll stop there and I'm happy to take some questions.
Thank you very much, Doina. Do we have time for one or two quick questions? Do we have any questions from the audience in the room or online? As a reminder, our invited speakers will be back for the panel discussion at 2 p.m. Yeah, there's a question.
Okay. Hi, Doina. Thanks for the talk. I was just wondering, how does this concept of affordances relate to pre-post conditions in like classical planning, like PDDL or those type of planning?
Yeah, so that's a very good question. One way to think about it is that preconditions in PDDL and other similar languages are a compact way to specify affordances because they tell you when an action or a macro action can be applied. And in what we're doing here, we're not being particularly smart about the how compacted this representation is. We're using these classifiers. In principle, we could do a lot better by using a more structured language for expressing.
Thank you for the great talk. And my question was about affordability. Is it a good idea to consider the states in the future where a possible action might be affordable?
Could you speak just a tiny bit louder, please? I have a bit of trouble hearing.
Sorry, too short for the microphone. So my question was around affordability. Is it possible if we consider the states in the future that might be affordable?
Yeah, so I think in terms of what's affordable, currently we think of this as being either states or state features. And we've done a little bit of work using sort of not full state information, but state features in principle, because the affordance is defined through classification. This is a natural extension. I think there's a lot of possibilities also to look at other things, like, for example, the history of states or any other sort of inferred information like latent state in the affordance. We haven't really explored that empirically yet.
Thank you very much, Doina, and thanks for asking questions, everybody. Let's give another round of applause.
Thank you very much.